In this session, I'll be going to discuss what is root locus and why we plot this root locus diagram. So that I can justify that by single statement, which is it is plotting system's dynamic characteristics. So what is system's dynamic characteristic and how we can plot that on real and imaginary axis. So to have an answer of it, let us have one example. So I will be taking one example in which we have unity gain feedback. So if system with unity feedback is given by GS is equals to K divided by S into S plus 2. So this is what the example which is given over here, and I'll be explaining what is root locus and why we need to plot it. So generally, if this is the case, in that case we'll be having characteristic equation of system. Right now I'm not explaining root locus method, but I'm explaining right now what is root locus and why do we need to plot that. So we have we have systems transfer function, and that is been given with unity gain feedback. So we can have a characteristic equation of this system. So characteristic equation of above system, that will be 1 plus GS HS is equals to 0. Here HS is equals to 1, the reason is feedback is unity. So we'll be having characteristic equation, and that is 1 plus K divided by S into S plus 2 is equals to 0. So this will be S square plus 2S plus K is equals to 0. So this is what the system, which is what we are having right now. Now in this system, position of characteristic equation, that is explaining, characteristic equation explains CS by RS is transfer function, and this is what numerator polynomial and this is denominator polynomial. So denominator polynomial, that has been explained by characteristic equation. So over here in this example we have characteristic equation, and that is what denominator's polynomial, and that denominator's polynomial explains position of poles. So when we talk about position of poles in this system, then that position of poles, that is changing with respect to value of K. Here position of poles, that is changing with respect to value of K. For example, if I consider K is equals to 0, so in that case pole's position, that will be S square plus 2S is equals to 0, means there will be two poles. One pole is at S is equals to 0, and other pole that will be at S is equals to minus 2. So let us plot that first on real and imaginary axis. So here we have real and imaginary axis, where here if I say this is 0, and here if I say there is minus 2. So in case of K is equals to 0, in case of K is equals to 0, we have pole's position, that is over here. Now if I consider pole's position for value of K, that is equals to 1. So if I say K is equals to 1, then characteristic equation, that will be S square plus 2S plus 1 is equals to 0. So in that case, I can say there are two poles, and that is at s is equals to minus 1. So s is equals to minus 1 and s is equals to minus 1. So there are two poles which is there at s is equals to minus 1. So what will happen over here? Position of pole that will be over here. Both of the poles that will be over here. Now, if I consider a third case for k is equals to 2. So if I take k is equals to 2. So in that case, this characteristic equation that will changes to s square plus 2s plus 2 is equals to 0. So it means this will be s square plus 1 is equals to 0. Sorry, s plus 1 whole square plus 1 is equals to 0. So ultimately that has to be s is having two roots. One is s is equals to minus 1 plus j1, and second root is minus 1 minus j1. So ultimately now this pole position based on value of k is equals to 2, that will changes somewhere here, where this is s is equals to minus 1 plus j1, and other pole that will be over here, that is what s is equals to minus 1 minus j1. So ultimately what we are doing is we are changing position of poles, and stability is even changing with respect to position of poles. So ultimately as we change the value of k, system's pole position that is getting changed. So root locus, that is a method which is what explaining a diagram where value of poles and zeros that is getting changed. So here if I say system's poles is starting from k is equals to 0 over here. Now this line that is moving in this direction as k is increasing, and once k is equals to 1, both of the poles that is reaches over here, and further if we increase value of k, these lines are moving in this direction. So this is how system's characteristic is behaving. So here by using root locus methodology, we plot system's dynamic characteristic where position of poles are moving with respect to value of constant, and this is what we are plotting it by using root locus rules. So here I am not explaining rules of root locus, but here what I explain is system's dynamic characteristic changes with respect to change in constant which is there in characteristic equation. So this is what the basic need, which is what we need to have it for root locus. The reason is when we use root locus methodology, there are some sets of rules. By using those sets of rules, we can easily plot this characteristic. When we plot this manually, we need to have computation so many times. The reason is it may be having more number of numbers for a plotting. So in that case, it will take more time to have a computation. But if we use root locus methodology, we don't need to have that many computation, and at the end we can have exact plotting of system's dynamic characteristic. Thank you so much for watching this video. In next session, I'll be going to explain rules of root locus. Thank you so much for watching this video.